Okay, so welcome back to AI for Robotics. I start the session also online, so we are good to go, I guess. Let me just share the screen. Okay, no. Okay, here we are. Okay, so this is where we stopped last time. And so you remember that we defined just a quick recap of what we saw last time and why. So we introduced propositional logic as a way to represent knowledge inside the head of our agent. Okay, so our purpose is to program intelligent agents. And we said, okay, one way to do it is to represent facts being true and false, and then encode them using propositional logic. We have a syntax to talk about sentences in propositional logics and to write them correctly according to some grammar. And we assign to these sentences some meaning. And intuitively, you remember I used the Boolean circuit analog in the sense that you can view a propositional formula as just another representation of a Boolean circuit. The Boolean circuit is, you are accustomed to see it graphically. Here we use some squiggles, but it's the same thing. And semantics, you can view it as just pushing some values to the input of the circuit and observing the output. Okay, so this is what it is about. So if you have troubles with the with the definitions here, you can always recall the Boolean circuit analog and think of connectors as gates and semantics as just supplying a value to the gate and observing the output. And as you can see, the truth table that we introduced is completely in tune with this analog. If you had the previous exposure to Boolean circuits, you know that you don't need all these connectors, okay? We said last time that even one single connector like NAND or NOR gates are sufficient to build all the other ones. But, you know, to make our life easier, here we are not building circuits in silicon. So to make our life easier, we introduced more connectors and defined their semantics. Remember that we are dealing with inclusive OR. So when we write OR, we mean something that is false only when both arguments are false. We are dealing with material implication, okay? So it's the kind of implication which is false only if the antecedent is true and the consequent is false. And we have seen that we can, of course, define other familiar connectors like exclusive disjunction, XOR, just by negating, for instance, the co-implication, okay? So this is what we saw last time very quickly. If you have any questions, I hope everything is clear, but if it's not, feel free to ask questions anytime. One last thing, we introduced this notion of assignment. So an assignment is just an evaluation given to the atoms, to the variable of the formulas. Once you have an assignment to the atoms, you can propagate it through the formula and get the value for the formula for the sentence. There's some special assignments, those that satisfy a formula. So those assignments that make the formula true, okay? The inputs that make the Boolean circuit emit 1 or true, okay? And those are called models, okay? So everything is an assignment. Each time you assign values to all the atoms of a formula, you have an assignment. Some of the assignments are models, okay? And now we'll see what happens when, for instance, a formula, a sentence has no model. meaning that no matter how you assign the variables, the outcome is always false. Or every assignment is a model, meaning that no matter how you assign the variables, the outcome is true. Okay, so we are going to introduce some more terminology that I spared you last time because it was already a lot. Okay, so this is very important because, as we will see, a little spoiler here, pretty much everything we need to do, every kind of reasoning that we are going to make in propositional logic will be reduced to satisfiability or unsatisfiability, okay? So this term will be used many, many times in the next few lectures. So what it means for a formula to be satisfied? Well, if the formula is satisfiable if it has at least a model, okay? There exists at least a model for phi. Okay, it doesn't matter whether there are more than one. Okay, the important thing is that it's non-zero. So there is at least one model that satisfies the formula. Okay. So for instance, all the basic formulas, those made with the connectors, are trivially satisfiable, right? So A and B, if I write A and B is satisfiable by assigning A to true and B to true, okay? Same thing for A or B. For instance, okay, this is the only one, okay? In the case of A and B, there is only one. Well, green was not a great choice, right? I'm using a different color. I should refrain from using green. Let's use red. So A and B is satisfiable by assigning B to true, and this is the only one. Okay, there's only one satisfying assignment for this. A or B is satisfiable. This is just to make some simple example, okay? In the case of A or B, there are three satisfying assignments, if you remember, every one except when you assign both of them to false, and so on. For instance, A implies B is satisfiable. For instance, if you put A to false, B whatever. Okay. B can be, once A is false, B can be either true or false, and this will be satisfied, and so on, right? And using the rules we have seen for semantics, we can you can build up a satisfiability. Now the question is, as we will see, it is easy to check that an assignment works. Just assign the values and evaluate the formula. Evaluating a formula, as we will see, takes polynomial time. It means it is efficient in the size of the formula. Finding a truth assignment is another issue, and as we'll see, this is slightly more complicated. There are other notions. You can extend the notion of satisfiability to a set of formulas. Okay, so here we have a set of formulas. A set of formulas is satisfiable if there exists an assignment, okay, that satisfies all of them. Okay, so in words, this gamma is satisfiable if and only if. This stands for its co-implication, okay? Sometimes you'll see this if, and this means if and only if, and it's just co-implication, okay? So a set of formulas is satisfiable if there exists an assignment that satisfies all of them, okay? Satisfies all of them, okay? This is what this definition says. So it's not enough that you can find an assignment for each formula. It needs to be the same. So if you have a set of formulas, you can say this is satisfiable, but you must find one assignment that is good for all. Okay. Now, that's the contrary, right? So a formula is unsatisfiable or contradictory. We will be using the same term if for every assignment it is not the case that the assignment satisfies phi. Let's make some example. So for instance, A and not A. It is easy to see that I'm saying at the same time that something is true and false, and that cannot be the case, right? So because if we try to assign A to true, then the formula becomes like true and false, which is clearly false. If you assign A to false, the formula becomes false and true, which is clearly false. Here I'm abusing a little bit the notation by introducing these constants, okay? But we said that we allow ourselves to do that, because once we have just a formula made with these constants, it's easy to see what's the result, okay? Okay. Then if you have, this is another important notion, gamma is a possibly infinite, well, right now we will never deal with this. So this is in fact parenthesized because we are not really, okay, logicians are into and mathematicians are interested in this kind of stuff. And it makes a difference whether you are considering finite set or infinite sets. So it is really important to make this fine-grained distinction, but we are in the engineering department here, so all we care is what can be implemented in a computer. So we don't really care about infinite sets. So it is there because from a logical point of view, that is the definition, but all we care about in reality is finite sets. So if all the sets we will consider when we say gamma is a set of formulas, we'll have in mind something that is finite. So if you have a set of formulas, you write this, see? So you extending the relation double term from formulas and assignments even better. Rather than extend extension, this is an overloading. set of formulas. Okay, so you might notice that it is the same symbol that we used to say that an assignment is a model of a formula. Okay, so there's a little bit of overloading here. We are using the same symbol in a different context. Now we have gamma, which is a set of formulas, and phi, which is a formula. And we say that the gamma entails phi, or that phi is a logical consequence or logically follows from gamma, if and only if for every model mu of the formulas in gamma, mu also entails phi. Okay. So what we have here, we have that mu needs to satisfy all the formulas in gamma. Okay. And also phi. If you can bring up all the models of gamma and you find out that they also satisfy phi, then this works. Okay. Notice that phi could be satisfied by other models. Okay, we are not saying anything about the models of phi. We're just saying that as long as all the models of gamma are also models of phi, this works. If you find just one model of gamma, which is not a model of phi, then this doesn't work. Let's make a very simple example of this. Okay, okay, let's say that gamma is defined as A, and A implies B. Okay. And phi is B. Very, very simple. Okay. So now it's a clear line of reasoning. Okay. A very easy syllogism that if you know A and you know that A implies B, then you also know B. Very easy. So we want to check whether and we expect that this is indeed the case, but let's see if it matches with our definitions. So what are the models of gamma? Okay, these are the assignments such that mu is a model of A is a model of A, and mu is a model of A implies B. Okay, this must be the same assignment. Now, in order to make A true, there is only a possible assignment. Okay, so mu satisfies A if and only if mu assigns A to true. Okay. So now you must take this for granted. Mu satisfies A implies B. If and only if either mu assigns A to false, or mu assigns A to true and B to true. But this one we can rule out, okay, because we already said okay, so this possibility of satisfying A implies B is ruled out by the fact that in order to satisfy A, we must have this. So the set of assignments that satisfies gamma is just one, okay? There is only one assignment. And clearly, mu also satisfies B. So the answer is yes. Okay, I'll go over it once more. This is very simple example, but you can expect to have more formulas here and more complicated consequences. We will see that everything can be reduced to satisfiability in a minute, but for the time being, let's work with this in order to make also some get a little bit acquainted with this language and how we reason about it. Okay, so this is a proof, a formal proof. Something you might not be totally accustomed to do it on yourself. You have been accustomed possibly to study proofs in calculus and physics, okay? This is a proof that we came up with by ourselves, okay? And this is what is, if you look at except the planning question, where you are expected to come up with a program, more or less, some kind of a program, in the two questions about logic in the final exam, you're expected to come up with a proof. Okay, so this is the kind of exercise, well, slightly more complicated than this maybe, that you might expect. But if you look in the past few exams, it is many times the case that the first question about propositional logic is proving about a logical consequence or modeling some situation and then proving about logical consequence, because it's the kind of reasoning that a logical agent, intelligent agent would do, right? So this is the kind of reasoning we are most interested in. So again, we have two formulas, A and A implies B, and this is our set gamma, and then we have our formula phi, which is just B. And of course, I mean, for this simple example, we can see our intuition is that B should indeed follow from the fact that you know A and you know that A implies B. But then we work out through the definition. So we know that this is true if all the models of gamma are also the models of phi. What it takes for a model to be a model of gamma, a model of gamma must satisfy all the formulas in gamma, okay? So I'm using two definitions here. The definition of entailment, which tells you that gamma entails phi exactly when all the models in gamma satisfy also phi, and I'm using the notion of what it takes for an assignment to be a model of gamma, which is the assignment must satisfy all the formulas in gamma. So it's two definitions of the previous slides that I'm using here. So first thing I ask myself is, what are the models of gamma? And so I work out my definition, and I see that my assignment needs to satisfy A, but it also needs to satisfy A implies B. Now, it's easy to satisfy A, you just put A to true. Here I'm using the representation of an assignment as a set of literals. So in order to say that A is assigned to true, I'm just saying that the set of literals in mu is A. If I'm going to assign to satisfy A implies B, I can do this either by setting A to false or setting both A and B to true. These are the two ways in which I can satisfy A implies B, but this way of satisfying A implies B is ruled out because I said that in order to satisfy the first formula, A must be true. So only one assignment is left standing. If to these sets of formulas I add not B, okay, the sets of formula would become inconsistent, as we've seen before. There will be no model that satisfies all of them at the same time. Okay, I'll make an example for it. But now I know that the whole set of assignments that satisfies A and A implies B is just one. Okay, and now I check whether this satisfies phi, and the answer is yes. Actually, in this case, it is also the only one that satisfies phi, because in order to satisfy phi, B must be set to true. Okay, but let's make another example.
Sir.
So now this time gamma is
sir,
again
I have a question.
A and A implies B. And phi is B or C. Okay. So we already know okay. But now it turns out that this assignment, which assigns B to true, also satisfies phi, right? Why? Because once B is set to true, C can take whatever value. Okay? Because this is a disjunction. So this is less obvious, but it's still true. Okay? So A implies and A implies B logically entails B or C, because this is what the definition says. All the assignment that satisfy gamma also satisfy phi. Yes. Wait a minute. Well, we did not speak about axioms yet because we are just making assumptions. So, but I mean, as long as there can be non-intuitive results, but as long as the definitions are satisfied, that works. Then, of course, it is up to you what you assume inside your logical agent as facts about the word, and given that, you will derive the consequences based on your reasoning. So for instance, if you assume A and not A, you'll be able to deduce anything, but of course also false things. Okay, so for instance,
Sir, I have a question.
this one is inconsistent. Okay. And try to think about it by yourself. It's not difficult, okay? But this set is inconsistent. Okay, let's see if we completed our sets of definitions. Okay, one more. This is the notion of validity. A formula is valid or is a tautology in propositional logic if every assignment satisfies it. Example. To be or not to be, okay? If A is assigned to true, then we have true or false, which is true. If A is assigned to false, then we have false or true, which is again true. So, short recap. To be satisfiable, you need only one model. A model is an assignment that satisfies the formula. Okay, so to be satisfiable, you need only one model. To be a tautology, you need that every assignment is a model. Okay, so satisfiability is there exists an assignment. Okay. And this one is for all. So here we have an existential, implicit existential quantification. And here we have an implicit universal quantification. Since here it's for all, we even remove the assignment from the symbol, and we just write the double term phi, because you don't need to mention explicitly which assignment is satisfying your formula. It's all of them. We can extend the notion of satisfiability to sets of assignments, but then you need to remember that you must find an assignment that works for all of them. Okay, so a model, there is a model for all the formulas. A formula is unsatisfiable if you cannot find an assignment for it. Now, we will say it even better, but maybe some of you also have the suspect that if you take a tautology and you negate it, what do you obtain? A contradiction. And if you take a contradiction and you negate it, you obtain a tautology, okay? If you have a satisfiable formula and you negate it, you don't know, okay? Because clearly, a tautology is also satisfiable, right? But not all satisfiable formulas are tautologies, okay? So a formula can be satisfied under some assignments and not under some others. So when you negate a satisfiable formula, you don't know, okay? But you know that a contradiction is not satisfiable, and the negation of a tautology is a contradiction. So if you can check satisfiability, you can also check tautology, and the other way around, okay? It's one problem is the dual of the other. If I have a decision procedure for checking tautology, an algorithm for checking tautology, I can also check satisfiability and the other way around. As we will see, we will go with satisfiability because it is somewhat easier to think in terms of finding assignments rather than proving that all assignments work. But it's really the same thing, because in a case of tautology, you can go and look for a single assignment that doesn't work, right? So if you had to come up with a procedure that decides whether a formula is a tautology, you try to find an assignment that doesn't satisfy the formula. And that would be the same as finding one that works. Okay, but this is a little anticipation to what we are going to see next, but just to be sure that we start understanding each other. And if what I said is kind of obscure to you, please ask questions. Okay, more about our notion of satisfiability and so on. Okay, if we have two sets, okay, and gamma prime is a subset of gamma. If gamma is satisfiable, then also gamma prime is satisfiable. Let's give some intuitions about this. Fun intuition. Okay. We are able to find at least one assignment that satisfies gamma, okay? But gamma prime has less constraints, okay, than gamma. What do I mean by this? I mean that you have less formulas to make happy, okay? So your assignment must make happy all of the formulas. Like you invite a bunch of friends, you have to make them happy by offering booze and something to eat and so on and so forth. If you have less friends, you have less tasties to accommodate with, okay? So this is the same thing. If you have at least one assignment that satisfies gamma, you take away some of the formulas, so you have a subset of gamma, then it is easier to satisfy them. There could be even more models at the point, but definitely the sets of models you had before still works. Okay? This is not meant to be a proof, it is just relying on your intuition, and we are giving this as a fact. Another way to remember this is that when the set of formulas becomes smaller, the potential models becomes bigger. Okay, so this is kind of the way it works. The less the formulas in gamma, the more the models could be. Okay, and even more important, this goes the other way around. If you were able to show that phi follows from gamma prime, then phi also follows from gamma. And 2 is easier to show because fact 1 tells us that let's call it mu of gamma is such that okay. So we know that from fact 1, we know that the models of gamma, which I write as mu of gamma, is a subset of mu of gamma prime. When gamma prime is a subset of gamma. And then we have the 2 pages, but I need only one. Let me delete this one. Then if mu of gamma is a subset of mu of gamma prime, and gamma prime implies phi, this means that for each mu in mu of gamma prime, okay, we have mu implies phi. And since gamma prime, okay, since gamma prime is a subset, sorry, since mu of gamma is a subset of mu of gamma prime, all mu in mu of gamma prime are also mu of mu gamma. Therefore, every mu in mu of gamma is such that mu satisfies phi. Okay. So if phi is a logical consequence of gamma prime, okay, we have that every mu in mu of gamma prime satisfies phi. This is what logical consequence means, okay? This is one part. But since we have that mu of gamma is contained into mu of gamma prime, okay, remember when we add formulas, we have less models. All the assignments that are in mu of gamma prime are also in mu of gamma. Easy. Mu of gamma is a subset, okay? So all of them are here. And therefore, that is okay. So I outlined the single steps. Okay. So this is about the definition of entailment. This is about subsets. And this is again from the definition of entailment. Yes. All mu in, sorry, yes. You're right. Yes. That's right. Okay, now it's correct. Thanks. So the other thing about demonstrations is that it's easy to get them wrong, but it's nice that it's a lot of us, so we can think about them together. Okay, so and this is nice because if we manage to prove that a subset of formulas, okay, entails a certain fact, that means our knowledge base entails a certain fact, then we can add stuff to our knowledge base and keep that stuff as a consequence of our reasoning. Okay, in fact, it is called monotonicity. In words, if our knowledge base contains some facts, okay, gamma prime, and we add more facts, gamma, superset of gamma prime, all the facts that could be derived before gamma prime implies phi are still derivable. Gamma implies phi. That's why we speak about monotonicity. Okay. Now, monotonicity is a little bit like the famous postulate in geometry that if you negate it, okay, nobody was able to show. If you negate it, you discover Riemann geometry, okay? So monotonicity is not always good. Think about an agent getting to know about birds, okay? And the agent might know the fact that all birds fly. Then you get to know about penguins, but penguins do not fly, okay? And this breaks monotonicity because you're adding a new fact to your knowledge base and it doesn't work that way. And in fact, there is a whole bunch of AI, deduction-based AI, which deals with non-monotonic logics that can tolerate this kind of issues with your knowledge base. And it's, as you may guess, it's an important branch in the sense that there are many issues in common sense reasoning where non-monotonicity is a property that needs to be taken into account. Does this mean that reasoning in propositional logic is useless? No, it works as long as we can ensure that we are dealing with a word where monotonicity is a good model of what's going on. So if you are modeling a word of digital circuits, or I mean, if you take the closed word assumption, so-called closed word assumption, you say everything I know is this, and I cannot infer new facts that will break my knowledge base, then it is fine. Okay. Here there are two questions. What is the shortest tautology? Well, this one is tricky. If you allow the symbols true and false in your language, like we informally did, then you have to have that as the shortest tautology, okay? So if you allow the symbol true in your syntax, then that's the shortest tautology. Otherwise, the idea is that you should try and build the shortest formula, which is still always true. And here, the answer is that with the connectives that we defined, it could be this. But since we have a connective, the connective material implication, you can shorten this even more, okay? So this is 4 symbols. This is just 3 symbols. There's also another one with just three symbols using the ones we defined, which is, it's easy. Think of the symbols you have defined. So what about A if and only if these 3 symbols? Okay, so this one is not, because it's 4 symbols, but A if and only if A. So if A is true, that is true if and only if true, so it works. If A is false, false if and only false, and it works. Okay. And these are the shortest. I mean, you cannot define anything with 2 symbols because that would be just negation and an atom, and not A is satisfiable, but not a tautology. Does there exist a set of formula entailing bottom? Well, let's see. right? That is the definition. But what are the models of bottom? Bottom is unsatisfiable, okay? So how can we, what kind of formulas should I put in my set gamma? For instance, therefore, to have gamma entails bottom, also mu should not satisfy gamma for every mu. Gamma is contradictory. Okay? For instance, what was suggesting your colleague was A and not A, or any contradictory sets of formulas. This means that, as we were saying before, if you push a contradiction in your knowledge base, no, then you can deduce everything in sense, including falsity. So in order to have a decent logical agent, you don't want your knowledge base to become inconsistent, because if your knowledge base becomes inconsistent, then your logical agent can deduce everything and also the contrary of everything, okay? Which is not very nice if you are trying to decide what to do in a robot or some other device. Okay, let's do this exercise together. So we have a set of 3 atoms, and we have an assignment. And now we know how this works. Okay. Okay. So let me make a new page here. So the assignment is A is false, B and C are true. Okay, this is our assignment. So the first formula is A implies not B or not C and B. Right? Right. Okay. So let's work starting from the atoms and build our value up. Okay. So what do we have here? We have that A is false, and B is true, and C is true, and B is true. Okay. So here we have an implication. So we should look at what is not B but it's an implication, right? So we are a material implication. So we already know that it doesn't really matter. Here we can have a formula with 200 symbols. It doesn't matter. If A is false, the whole material implication is going to be true. Okay, so we already know that this is going to be true. I'm not even looking at the not B. Okay, and so this is what, in case you find yourself evaluating formulas, this is nice if you do it. I mean, try to save some time. Okay, true and true. We know that the conjunction is true. Exactly. So we can even avoid the good point. We can even avoid this evaluation. So I'm writing it. But there's no need to evaluate this, and there's no need to evaluate this. Okay, and so we already know that the whole thing is true. Good. Let's check formula number 2. Not A implies not B and C. Okay, again, A is false, B is true, C is true. Okay. So not A is true, and so we need to check what happens here. Not B is false. Okay. So true implies false. This is false. And the negation of false is true. Am I right? Now it's true and true, which is true. Okay, so this was the negation, negation. This was implication. This was negation, and this was a conjunction. Okay. 3. Okay, this one is, let me add another sheet here. Okay, so 3 is not A and not B. Implies A and not C. So again, A was false, B was true, A was false, and C was true. Okay, we can save us some time here because we already see that this is false. It's a conjunction, so the whole thing is false. We don't need to evaluate this. Now this is false, so we need to see what happens here. So not A is true, but not B is false. Okay, so now we know that the whole conjunction will be false. Okay, so this is the negation, and the conjunction. Now, it's false implies something, so we know that this whole thing is true. And in fact, if we had started our evaluation from the first element, we could have spared us the evaluation of this. Okay. In hindsight, of course, I mean, you're always wise when looking back in the past, but sometimes you just don't know. Okay, so I'm sparing you number 4, which is quite easy, I would say. So both C and B are true, which means that the formula is clearly true. Okay, and notice that I guess pretty much every one of these formula is satisfiable, but is not a tautology. We should check that. In fact, not all assignments satisfy them, but we will spare this when we have the procedures to do it that more quickly than now. Okay. Okay, here we have some more terminology, but it's an important one because we will be using this later on when we introduce transformations. We will see that in order to write programs that deal with the satisfiability of formulas, we need to transform our formulas. And that transformation, in order to be made efficiently, we need to introduce variables. So we need to take into account this. So you can say that two formulas are logically equivalent exactly when they have the same models. Okay. An example is and we used this implicitly before to write our shortest tautology. Okay. But for instance, A implies A is equivalent to not A or A. And in fact, all the models, this is a tautology, this is also a tautology. Okay. A corollary of this is that all tautologies are equivalent if they have the same atoms. Okay, so if I take two tautologies and they are built over the same set of atoms, they are equivalent. So tautologies built on a set of atoms form an equivalence class. You can substitute each of them for each other because they are simply logical equivalent. And you can substitute them with true, which is also tautology. Whereas two formulas are equisatisfiable when, given that you can find an assignment for phi 1, you can also find an assignment for phi 2. Mu 1 can be different with respect to mu2, okay? They don't need to assign the same variables. So clearly, if two formulas are equivalent, given the definition, they are also equisatisfiable. Just take mu1 and mu2 to be the same assignment. But the other way is not true, okay? And this happens, for instance, if two formulas are built on different sets of variables. If two formulas are built on different sets of variables, maybe you can find an assignment for the first one, and you can see that at the same time you can find an assignment for the other, and also the other way around, okay? So it should go both ways. But of course, they are not equivalent by definition because they should be on the same sets of variables, okay? So equivalence implies equisatisfiability, but not the other way around. And if two formulas are logically equivalent, okay, you can replace them as subformulas in another one and get a logically equivalent formula. We will see some of this in the next few slides. So that are not completely satisfied. Yes, of course, you can have satisfiable formulas that are not equisatisfiable. Yes. As long as you can find an assignment satisfying phi1 and not be able to extend it to an assignment that satisfies phi2. Okay, so here an example of equivalent formulas that can be used, for instance, to replace in other formulas. Okay, we already seen this. In order to check that this is indeed equivalent, we should show that all the models of this are also models of this. Okay, so proof that okay. Okay, so this is the semantics of phi1 implies phi2, okay? And we know that we have this is true, this is true, this is false, and this is true, okay? So this is the semantics of the implication. Now, let me, here we have not phi1 and not phi1 or phi2. Okay, so not phi1 from the semantics of negation is true, true, false, false. And now we consider this one and this one. So here we have the not phi1 is true and phi2 is false. Okay, so the disjunction is true. Here we have that phi2 is true. So again, this is true. Here we have that they are both false, phi2 and not phi1. So this is false. And here we have that one is true and the other is false. So it's true. Okay. So let me write, this is the semantics of implication. This is the semantics of negation. And this is the semantics of disjunction. Okay. And here we can see that there is only one model which falsifies both. It's only one assignment. So this is a proof that the two formulas are equivalent. As we will see, we will learn how to make proofs without resorting to truth tables. Why we do not want to resort to truth tables? Because if you have n variables in your formulas, then the truth table has 2 to the n rows. Okay, so truth tables become practically unfeasible starting from n small. As we will see, it's an inescapable worst case. The exponential blow up in complexity. But as I said, it's a worst case. So in principle, one can do much better than truth tables. Whereas with truth tables, you know that you will be expanding 2 to the n rows each time. Okay. Let's look at some other equivalents and see if they are obvious. Okay, now the negation of phi1 implies phi2 is logically equivalent to phi1 and not phi2. This works, right? If you remember, there is only one assignment that falsifies phi1 implies phi2, and that assignment is when we have phi1 true and phi2 false, which is exactly the only assignment that satisfies this formula here. Okay, so the only assignment that falsifies phi1 implies phi2 is not phi1, sorry. Okay. Phi1 if and only if phi2, we said that this is coimplication. So phi1 if and only if phi2 is logically equivalent. Notice that we use this symbol to distinguish from the syntax coimplication. To phi1 implies phi2 and phi2 implies phi1. But we have seen that phi1 implies phi2 is logically equivalent to not phi1 or phi2. So this is logically equivalent to not phi1 or phi2, and this is not phi2 or phi1. Which is what you have here. Okay. Okay, there's one step more if you want. We should prove that phi1 or phi2 is logically equivalent to phi2 or phi1. That means that OR is commutative, okay? But it's clearly the case. And this is the negation of phi1 and phi2, and as you can see, is equivalent to several other formulas. This is the disjunctive. No, sorry, not disjunctive. Exclusive. Okay, and for any formula that we already mentioned this, there is one equivalent using only negation, conjunction, and disjunction. Even more, you can use only negation and disjunction, and so on and so forth, through this logical equivalence thing. But this is the set we will be using when we will work with the representation for computers. Okay. Okay, and we stop here because this is a set of statements that next time we are going to prove, so it will take us some time. That's it. I will see you on Monday, right? Next Monday.